Hello everyone, and thank you for attending today's webinar, How to Reconstruct Pre-Transformation Microstructures in OIM. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these at the end of the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer via email. A copy of today's slide deck and some links to additional materials are available in the resource list. The widget looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of your slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available in approximately 1 day after the webcast is over, and it can be accessed via the same audience link that was sent to you earlier. Now I'd like to introduce the presenter for today's webinar, Dr. Stuart Wright. Stuart was first introduced to EBSD as an undergraduate student at Brigham Young University, working with the first system in North America. He then moved on to Yale University to pursue a PhD under Professor Brent Adams. His thesis research focused on automating the EBSD technique. This effort led to the first fully automated EBSD scans in the fall of 1991. After graduating, Stuart joined Los Alamos National Lab and continued work in microtexture and texture analysis using both the OIM technique and conventional X-ray diffraction. Shortly after, TSL was founded. Stuart left Los Alamos and joined the startup company commercializing the OIM technique, working primarily on software development. He continued in this role through the purchase of TSL by EDAX. The original OIM system at Yale could index approximately 1 pattern in 3 seconds. Modern systems have come a long way since those early days, with speeds now exceeding 4,500 index patterns per second. Stuart is closely involved in the continued development of the technique, as well as in working with scientists all over the world and applying the technique to their materials research. Now over to Stuart.
Thanks, Jonathan. Welcome, everyone. As we've been waiting to start the webinar, I've watched the registrations come through and seen many of you that I recognize, and just wish we could be together at the conferences and things, but I'm happy that you joined us and give you best wishes during these difficult times. Today I want to talk about what we've done to reconstruct the pre-transformation microstructures in OIM. This is part of our new 8.6 release of the software that should be, we're hoping by the end of this week actually, to have it officially released, but we'll at least have it out by the end of the month for sure. So what we're talking about is when a material undergoes a phase transformation from one crystallographic phase to another, a grain may transform into several different crystallographic variants. So as an example, consider austenite, the austenite to ferrite transformation in iron. So there are several different ways or orientation relationships we could consider, but if we consider the Nishiyama-Wasserman relationship, which is 111 planes parallel to 110 planes between the FCC and the BCC, and then 112 planes in the FCC to 110 planes in the BCC, that's the alignment we expect. And so a grain could break into several different variants or transform into several different variants. In this example, I'm showing 6. And so you can see that a grain of one single orientation would be transformed into groups of variants in 6 different crystallographic orientations. So the objective we have is often what we can see or what we receive when we polish our sample is we see an as-scan microstructure that shows all the variants. And we'd like to be able to reconstruct and know what the microstructure looked like before that transformation to get at information like grain size, for example, in the parent microstructure. And so we know the orientation relationship, or we assume an orientation relationship, and then our goal is to reconstruct the microstructure. So we have an inverse problem than what I showed in that first slide. We have planes that we know are in parallel, and here's an example of 110 planes in an FCC structure parallel to the basal planes in HCP. and the 112 parallel to the 112 bar O in the HCP. And you can see now there would be 6 potential parents for that orientation relationship. So it's not a one-to-one. We can't just say, oh, here's the orientation and here's one parent. There could be 6 candidate parents to consider. So the basic algorithm kind of follows the following, and we're following an algorithm that was set forth in a paper by Ranger and his colleagues, some of which of you I see on today. And so I've used that algorithm to kind of work to implement into OIM. So we didn't try to reinvent the wheel. So let's say there's 3 neighboring variants here, and here's the list of possible parents that would be for those 3 different variants. And so if we look at those 3, we see there is one that's common to all 3. There's another one that's common to the red and the blue variants, but not to the green. And so we assume that one orientation there that's common to all 3 is the most probable parent, really for all 3 of those. And now I've shown this for a triplet of 3 different variants, but we actually do this just to simplify the problem. We actually do the same kind of thinking for all the neighbors of one variant or one child grain, not just 3, but all the variants that neighbor it. Do this process. And then we classify each as a high confidence parent, an ambiguous parent, or low confidence parent, depending upon basically an argument of how similar in this Venn diagram, how many times it appears relative to other orientations in the neighboring variants. So then the next goal is we assume the HCPs, the high confidence parents, are the most likely answers, so that looks good. So we try to grow those then into the other neighbors, the ambiguous and low confidence parents. Perhaps they appear farther down the list in those, that same orientation. So we can use that argument to grow them. And then we basically repeat that, but instead of using just the first nearest neighbors now, we actually consider also the second nearest neighbors and repeat the same step. And that then allows everything to grow, and you end up having back transformed essentially all of the our original as scanned microstructure. And then we can use some arguments to, if there's any that we didn't actually catch, we just do a simple argument based on looking at the nearest neighbors and using their orientations. So we do use the average orientation of each child grain as opposed to trying to do them on a point-by-point basis. And as we reconstruct it, we're actually assuming the parent grain orientations are constant during this grouping algorithm. And then we relax that at the end on a variant-by-variant basis. And I'll show some more examples of that. And so you end up, this is kind of the microstructure on the left is where we start, and then we go back and look at each child variant. And then if you want, you could actually go on a point-by-point basis using the identified orientation relationship at each point to reconstruct the microstructure that way. There's some argument as to which of these, at least some arguments I can think of as to which of these I would prefer. There are some times actually where I think the figure on the left is good, and other times where I think the figure on the right is well. And I'll show one example of why the figure on the right I think is interesting. Just to compare our results with those of others, I'm using the same data set that Ranger used in that original paper. And you can see we have a good match. There's some subtle differences, but we have a pretty good match. There's another paper by Lionel Germain, who's also part of the group of the Ranger paper, who I think has kind of the gold standard for reconstruction at this point. And you can see there's still a pretty good match with his work as well. There's some new work by Stephen Niscoda and Eric Payton and others at Ohio State, and you can see theirs is a little different, but it's still, the basics are there, especially in terms of, say, average grain size and things. I think if you had a larger area scanned, then the grain sizes would probably match up pretty well. on average. This data that we're using is courtesy of Matt Merwin at the U.S. Steel Research and Technology Center. Thanks to him. I did some experiments where I used other known orientation relationships for steel, and you can see the results there. The top row in the middle is the Nishiyama-Wasserman, seems to be the best match, although pitch is relatively similar. Some of the others didn't seem to reconstruct very well at all. But it is interesting to do this. I actually tried an algorithm where I didn't assume you could put in multiples, and it did a little better than the Greninger-Troyanos, but it didn't do as well as just using Nishiyama-Wasserman by itself. So one of the things that comes into play is a tolerance angle. How closely do two neighboring, the candidate parents match? And so I played with looking at 3 degrees versus 5 degrees versus 7 degrees, and you can see the results there. There are cases, I think, in some microstructures where smaller is going to be better, and in other microstructures where the larger will be better. And it simply may take some experimenting to find the best approach. I've also tried using, trying to refine the orientation relationship. So I start out with Nishiyama-Wasserman and then refine it using an example from a thesis from Tampere from Misonen. And you don't see a lot of difference here. You do see definitely some smoothing within the reconstructed grains and the orientation, as you would expect. But I'll show an example, another example later of where this refinement can be helpful. There's something called the minimum probability ratio in Ranger's paper, and this comes about because the orientations of the candidate parents are calculated for each child. And then the neighboring children of one child are checked to see if they have the same candidate parents. And so there's this minimum probability ratio that says how well the two lists match between two neighboring child grains. And you can use that as a criteria during this classification of the points as high confidence, ambiguous versus low confidence. And so you can see the results of using different values for that. And it tends to, as you go to larger values, you tend to get rid of the little tinier grains, which can actually be positive, but it also tends to strip away some that I think look like probable good variances, particularly on some of the twins in this microstructure. So we wanted to come up with a way to check and see if what we were doing made any sense, because we don't have the original microstructure. We don't have the right answer. We're kind of guessing at it, approximately. And so we had some data from a case study we'd done on in-situ phase transformations in Cobalt. For Cobalt, we're looking at an FCC to HCP transition. The transition temperature is around 422 C, as you see there. And you can see we were able to capture partially transformed microstructure in that one EBSD scan there at the center. And you can see patterns from both the beta and the alpha phases. So we were doing experiments at the time. We were really just testing the stage, but it was kind of fun. You could watch this microstructure transform, and we would just keep scanning over and over again while changing the temperature back and forth from room temperature to an elevated temperature. And you can see the microstructure go back and forth. First time I'd done anything like this, and it was interesting to me to see that the same microstructures, the same variants were selected every time, and then the same parents as well as we went back and forth. Those of you who work in phase transformations more than I do probably would understand that better, would expect that. But we were taking a look then to see if we could capture some of the details of phase transformation. This is a good example here where we have a partially transformed microstructure, and you could actually go in and look at patterns and see that the basal planes were aligning with the 1-1-1 planes, and you could see that in the pole figures and in the patterns themselves. So that was kind of a fun exercise. But in terms of what we're doing today, this allows us to look at the transformed and both the parent and child microstructures, and then compare it against the reconstructed that we did with our software. And so you can see the ambient result scans there, or at least one selection. from the series we did, and you can see all the different variants, and you can see both the retained alpha orientations, or the alpha orientations as well as the retained beta. And then at high temperature, you could see the retained alpha and the beta. And then you can see our reconstruction. So in the ones that left, the set at left, that bottom right microstructure should, or those on the bottom row, should match the reconstructed. And you can see it's a good match. There are some differences, but you can see that for the most part, we have recaptured the microstructure, including the twins. So that gives us confidence that what we're doing is working and that our approach is valid. So then we received some data on additive manufactured Ti-6-4. And so it's a very kind of cool looking microstructure. It's for a biomedical implant device in this case, and it's been fatigue tested. So we indexed it, got nice results both at a low and a high mag result, and then we wanted to look and see if we could reconstruct the microstructure. And even though we really don't know much, we know this looks like it's undergone a phase transformation, but we really didn't know anything about it when we received the sample. I would assume those who work on these materials would understand this and know this microstructure better, but it was an interesting for us to take a look kind of sight unseen. So for Ti-6-4, we have a phase diagram there on the left where we have an alpha phase, which is hexagonal, and a beta phase. And so from those microstructures, we do have a little bit of the retained beta. As you can see there, the little yellow specks that you see, it's hard to see it. You have to really go high mag to see those well. But if you look closely, you can see the orientations in those retained beta phase. And so that can be helpful because then we can start to infer, we get an idea of what the grain shape looked like beforehand and what the orientations were, and we can once again check to see if what we have been doing makes sense with our reconstruction. So here's the example, the as scanned data on the left and then the reconstruction on the right using that assumed orientation relationship you see there. We did get pretty much, there's a little bit that didn't get reconstructed, but we pretty much got it. And so we were pretty happy with those results. And there are some very interesting things there in that you see some color gradients within some of the grains, and that's an indication of orientation gradients. And if you've looked at some of the AM, the additive manufactured microstructures, you get these kind of unusual microstructures, at least compared to the kind of stuff we're used to seeing. But this is what they tend to look like. So we were pretty happy, but we wanted to check because we weren't totally sure that what we had done is correct. But if you look really closely here, and I hope you can see it on your screens, you can see that the colors match between the reconstruction and the retained beta. And that's a positive then check that we have a good match. And we've gone through and looked at the orientations. The color here is, these are what we call IPF maps, an orientation map that shows the orientation of the crystal axis parallel to the normal direction of the sample. And so there can be rotation about that axis, so we don't know if it's a one-to-one orientation, but with some quick checks, we do have a good match, not just in the color, but in the actual orientations in 3D. This one grain here is if we go back, sorry, the previous slide, you can see that grain that's purple to a pale colored purple. And you can see there's quite a change in color from one end to the other. So took a look at that, and you can see then that that's from, at least from the average orientation of that whole spec, there's about 7.5 degree difference in orientation from the extreme to the most extreme departures from the average orientation. And that's kind of interesting because that tells us then that the reconstructed grain seems to have a fair amount of deformation that to cause that change in orientation that we've talked about before. And so that just shows an example of, even though we have a departure in orientation with that much spread, we're able to still reconstruct the grain, which is good news. So the results I've been showing so far have been with orientation refinement that I mentioned earlier. If you look at it without, then that you see that you get more discrete steps across the grain than you do in discrete steps in orientation than you do when you do orientation refinement. Also in this example, I talked about, I used a larger tolerance angle, and that came about because of these gradients in orientation within the parent grains. So just as an example, we've implemented this into, like I said, OIM Analysis 8.6, which I hope is out by the end of the day, frankly. We're just finishing that. That's good news. So the user interface is pretty straightforward. You just select the data set that you want to perform reconstruction on, and then you enter, if both phases are there, you can select them. If not, then you can load what you think the parent phase should be. You can enter your own orientation relationships. Depending upon the phases you've chosen, we will try to pre-populate it or allow you to pre-populate it with various ones you can see here for steel. I've got the Bain, Nishiyama-Wasserman, the pitch, Kurjamoff-Sachs, and the Grainger-Triano variants. And then you have the other reconstruction parameters I talked about, the tolerance angle, the minimum probability ratio, and then whether you want to do the orientation refinement or not. And there's a few other things you can do, and I'll show some examples of why you might want to do that. So in OIM, I think it was 8.5, we created these ideas of correlative microscopy values. And basically what they are the ability to add custom fields into your data set at each point in your data set. And originally we thought of that for the reason of correlative microscopy. Maybe you want to match in some WBS data, some CL data values, some kind of value that you want to add in. So we've adopted those, that flexibility for the reconstruction algorithm, and we're populating them currently. The idea we had was to populate them with the number of contributing children to each parent grain, and as well as an identifier. I'll come to that. And so since you have that, then you can create maps, charts, or all the tools of OIM analysis and use that information to investigate and characterize your material. So like I said, we actually record 3 different CMB, correlative microscopy values, within the data sets. In the original data set, the child grain microstructure, we record the ID of the reconstructed parent. In the reconstructed data set, the new one, we also have the ID of the reconstructed parent, as well as the number of children per parent grain. Keeping the idea of the reconstructed parent is really nice, because then you can isolate and look at the variants that contributed to the reconstructed parent on a one-to-one basis and get a feel for what your microstructure looked like. And I would expect us to expand some of these CMB values in the future. We have a few ideas we haven't implemented yet. I mentioned the orientation assignment. You have 3 different options. You can do a single orientation per reconstructed grain. You can do a variant by variant orientation based on the identified orientation relationship, and that's the center picture you see there. Or you can do point-by-point orientations based on the identified orientation relationship. And you can see the results there. And I think the point-by-point is interesting because it, in terms of looking at those grains that have strong orientation gradients in them. You can also do some orientation smoothing after the fact if you wish, depending on what kind of orientation assignment you selected. I showed no smoothing for the variant approach to orientation assignment there on the left, followed by 1 iteration, which at this scale you really can't see much. I had to go out to really 25 orientations before you really see much in terms of the smoothing effect. But if you feel a need to do that within your reconstructed microstructure, that's possible. You can also, obviously we end up with a few small grains here and there. You can remove those just simply based on argument that I don't believe the small stuff. Maybe it's dust particles on my sample or something else where I just didn't get good patterns for some reason. And so you can remove the small parent grains just based on a % of the average. In this case, I use 10-degree boundaries, and you can see we go from no removal, 2%, 4%, 8%, and you get rid of some of the data, of the small grain stuff. So in summary, I think we've done a good job implementing the algorithm in OIM. It compares well with the other algorithms that are out there. And from the experiment so far, we feel like it does pretty well, even when the parent phase, when it has minimal orientation spread. It does pretty well actually when there's a pretty strong orientation spread. And the orientation refinement helps in that case. This code is multi-threaded. It's relatively fast, faster than I thought it was going to be when I originally started. I've also found that having some of the retained parent phase does help quite a bit. Not only does it help give you some confidence in your results, but it helps as a seed as well for the parent grains. And at this point, the algorithm is purely crystallographic. And obviously adding some morphological analysis would help so we don't get such tortuous boundaries in some of our grains. And you see that in some of the other algorithms that are out there. And like I said at the beginning, this is work that's been going on for quite some time. There's been a lot of good papers, and I've relied on some of that work. And I just wanted to give representative papers from several of the research groups that have been involved with this and thank them for their pioneering efforts that have helped us get to where we had something that was commercially available. And I hope convenient, as it sits within OIM and you can work with the same data sets and the same workflows that you're used to working. But I'm pleased to see so much work in this arena and hope that it continues and we can improve it even more than what we have done so far in the future. So with that, I will close, and thanks for listening in. There is one question I'll try to take a quick look at. The question is, what will happen if some child orientations do not have orientation relationships with the parent grands? In other words, during reconstructive or diffusive phase transformation. We haven't dealt with that situation, and this software is assumed with the way we've done this that it does have an orientation relationship. And so we would not be able to handle a material that goes through a phase transformation where you don't have a strong OR, or even if you have unknown ORs. Like I said, I tried to play with that a little bit. I think point you to the work of some of the others. I know Steve Niscota's taken a look at that a little bit. He and Eric Payton's work, their group, so you might want to take a look at that. I don't see any other questions, just some people saying thank you. I appreciate the feedback. If you do have questions, don't be afraid to send us an email. We'd be happy to try to help out and look for it in the next version of the software that you receive. And if you have questions, please reach out to those who choose our applications group, and they can help with that. As for, there is one more question that just came through before I close. How good is this reconstruction for tempered steel? So far, I've only looked at the one microstructure I've shown. I would have to do some experimenting with that, and we'll go from there. And boy, now the questions are coming in. Another one: do we have a way to selectively activate different variants? Not manually or anything like that. So far, I'm just focused on you can select different ORs and see how that works out for you and do it. You'd have to do it iteratively to find the right OR for your sample. So thanks to everyone. Hope you have a great rest of your day, and look forward to seeing you as we have starting to be optimistic that we're going to start seeing each other at the conferences again. Take care, everyone.